Not all stars shine, but some still burn with promise. We spend a lot of time thinking about bright and shining things in the cosmos, great blue giants blazing like cosmic blowtorches, or warm yellow suns like our own. But the universe has always had a soft spot for the dim and the quiet. Lurking between the stars are objects too big to be planets, too small to be stars, and just right for every science fiction writer who ever wanted to ask, what if home was a place without a sunrise? These are brown dwarfs, the failed stars that never quite made it to hydrogen fusion, but still glow with their own internal heat. They shimmer rather than shine, embers in the galactic night, whispering infrared warmth into the void for billions, even trillions of years. And as it turns out, these dim wanderers may be some of the most common stellar objects in the galaxy, more numerous than sun-like stars, more elusive than planets, and just possibly some of the best long-term real estate the Milky Way has to offer. Today we'll be asking what it would take for humanity to colonize these faint and lonely worlds, how to build habitats around an object that barely glows, how to find enough energy in a place where daylight never really arrives, how moons, magnetic fields, tidal heating, and megastructure engineering can turn a failed star into the beating heart of a thriving deep space civilization, and why brown dwarfs might be some of the earliest interstellar civilizations, as well as the perfect homes for late universe cultures, hiding in the dark long after the ordinary stars have grown cold. We'll also introduce two new megastructures, the Dawn Belt Array and the Equinox Shell. We often say that humanity is a tough species, and surely we're stubborn enough to build a civilization anywhere, even around a star that never quite got started. So let's take a journey into the quiet half of the galaxy and explore the possibilities of living around failed stars. What a brown dwarf is. Before we get into colonizing brown dwarfs, we should probably clear up the biggest misconception baked into the name. Brown dwarfs are not brown, not even close. In visible light they tend to be deep red, magenta tinged, or even a dull purple, and most of the time they are so faint you wouldn't see any color at all. They simply look like a smudge of near-infrared heat, the astronomical equivalent of a warm coal under a heavy fog. They absolutely give off light, and in the visible range too. These are the bigger mass ones, an L-type. The biggest are around 2000 Kelvin or even higher, but only about 1% of that light is in the visible rather than infrared ranges, and it goes down from there. That's enough to light a moon just fine, or maybe a planet. An object orbiting a brown dwarf could be argued to be both. And because so much is in infrared, places near it would be more dimly lit than their temperature would imply, their eternal twilight gloom rather comfortable. And it would be eternal too, as any planet or moon, whichever you choose to call them, around a brown dwarf would certainly be tidally locked. So one side under twilight gloom and the other eternally dark. But even the coolest brown dwarfs would give off enough visible light that if you were near one in the utter dark of the void, they'd be quite visible. Even the dimmer ones might only glow a couple orders of magnitude brighter than the starlight on their surface. As a reminder, astronomers classify stars by temperature, running from the hottest blue-white giants to the dimmest red embers, using the spectral sequence OBAFGKM. Each letter covers a temperature band, and within those bands we subdivide further using numbers from 0 to 9, with 0 marking the hot end of the class and 9 the cool end. Our own sun is a G2 star, sitting about 5800 Kelvin, while an M9 red dwarf would only be a few thousand degrees. These subclasses are not perfectly even slices of temperature, but they track how atoms and molecules behave as the furnace cools. And the sequence doesn't end with M dwarfs. It keeps going to infrared with 3 more categories, L, T, and Y dwarfs, for objects too cool and dim to qualify as stars at all. I think we could skip the brown dwarf name, given it is wrong and already has 3 distinct subcategories with different actual colors, though in my personal opinion, every dwarf star category except white dwarfs should be retired. Yellow and orange dwarfs are bigger than the majority of stars, so calling them a dwarf is weird, and red dwarf and brown dwarf categories are just too broad. For one thing, they include virtually every star. Plus, big M0 dwarfs have more in common with K-type stars than dimmer red dwarfs. The name brown dwarf dates back to the 1970s when astronomer Joe Tarter proposed a label for objects too small to sustain hydrogen fusion. The trouble is that brown isn't a real color of light. There's no brown wavelength in the spectrum. Regardless of mass, they're almost all of them about the same size as Jupiter, which is itself brown, so it's not the worst choice. Magenta or deep red would have probably been much closer to the mark, but this is the nature of scientific classification. You name things early, when you barely understand them, take your best stab at a useful term, and never get some of it wrong. Asteroid, for instance, means star-like, which is a very absurd term for something that's a small microplanet. Gas giants suffer from the same problem. Gas giant isn't really accurate, since they're overwhelmingly fluid giants, and only the outermost layers are gaseous in everyday sense, and may probably have solid cores too, so the gas portion of a gas giant is probably the smallest portion of the 3 types of matter that make it up. Yet the name stuck. We likely need that distinction anyway, because everything from Jupiter's mass up to a small red dwarf, about 80 times Jupiter's mass, ends up roughly the same size. That whole regime behaves as one family of highly compressed, degenerate fluid worlds. We treat brown dwarfs as occupying the mass band between 13 and 75 or 80 Jupiter masses, with 13 marking the point where our models predict deuterium fusion begins in the core. That threshold is mostly theoretical, since brown dwarfs are extremely dim, and even the faintest red dwarfs, the M9s, are hard to measure precisely. M-type red dwarfs themselves range from about 75 to 80 Jupiter masses up to 500, a 7-fold span that makes them the broadest stellar class, other than black holes. This is part of why I often suggest we need to divide them into 2 categories on either side of a quarter of a stellar mass, which is where the changeover point between being fully convective likely is, which means they stir their contents up entirely and thus never run out of fuel in their core till they are all helium, and become what we call a blue dwarf, a type of star that won't come into existence for another trillion years. Even the bigger red dwarfs live much longer than the universe is old, and that means they also dominate the galaxy, partially because they live essentially forever. None have died yet, and star formation tends to favor small objects over large ones, as does planet formation. For those same reasons, we expect brown dwarfs to be nearly as common as red dwarfs, perhaps even as common as every other type of star combined, and that makes them far more relevant for long-term human settlement than they're usually given credit for. They often get lumped in with rogue planets or generic gas giants, cold, drifting dim objects between the stars, but as we'll see, the colonization options around brown dwarfs are a very different story. But brown dwarf is what we've got for now, and in recent years we did with them what we should have done with red dwarfs and gave them distinct categories. So let's look at what the subtypes are. In descending order of mass, loosely speaking, brown dwarfs come in spectral classes L, T, and Y, each with its own peculiar glow. L dwarfs, red embers with mineral vapors. L dwarfs are the warmest of the brown dwarfs, glowing a deep crimson or burgundy that sometimes even tips toward magenta in visible light. I tend to think these objects have some legitimate claim to being stars, rather than merely substellar bodies or planets with delusions of grandeur. One important thing to remember about brown dwarfs is that their classification is based on temperature and luminosity, not mass. They cannot sustain normal hydrogen fusion, only deuterium, and they tend to exhaust that fuel within 100 million years or so, after which they cool steadily. That means a high-mass brown dwarf can still end up as a cooler T or Y type later in life. At the upper end, around 75 to 80 Jupiter masses, a brown dwarf crosses the threshold into a true red dwarf, though even that limit depends on metallicity. As a reminder, astronomers call anything in a star that isn't hydrogen or helium a metal, and metallicity gradually increases over cosmic time as supernovae enrich star-forming nebulae with heavier elements. This matters on the low end as well. The 2010 paper, The Deuterium Burning Mass Limit for Brown Dwarfs and Giant Planets, found that the minimum mass required to ignite deuterium depends strongly on metallicity and the object's initial deuterium abundance. Newly formed brown dwarfs with higher metallicity than our Sun might burn deuterium at only 11 Jupiter masses, while old, metal-poor objects formed in the early universe might need 16 Jupiter masses, especially if they've already burned through much of their initial deuterium. In general, higher metallicity objects fuse more slowly and live longer, because those heavier elements interfere with hydrogen fusion. Thus, a brown dwarf that was just a little bit short of what needed to become a red dwarf would not instantly become a star just because it absorbed a large mass planet like Earth that tipped over the edge, since Earth is primarily made of heavier elements. We'll return to the low mass Y-type shortly, but the key takeaway for now is that mass and temperature do not map cleanly across these categories. There is a genuine overlap, and brown dwarfs can wander across the spectral classes as they cool. Ls can begin as low as 30 Jupiter masses, while Ts can be anywhere from 20 to 50 Jupiter masses. L-type temperatures run from around 2500 Kelvin at L0 down to 1300 Kelvin by L9, a span where ordinary rock-forming minerals stop behaving like solids and begin behaving like vapors. They are bolometric luminosity, which is how much light in all wavelengths it emits, visible or not, and thus including infrared, fall around 10,000th to 100,000th of the sun's output, and only a tiny fraction that emerges as visible light, on order of 1019 to 1021 watts, enough for a faint red glow, but still hundreds of thousands of times dimmer than the sun to human eyes. Though keep in mind that's still hundreds to thousands of times brighter than Earth is. For an L0, its effective habitable zone is 100 times closer to the sun than we are, but that's closer than most moons on bigger planets, about 150,000 kilometers to a little under a million miles, and L0 is around 20 times brighter than an L9. A handy thing about brown dwarfs is they are almost identical in size. As they gain mass, they grow denser, so for a decent approximation, you can determine relative luminosity by dividing the temperature and raising the result to the fourth power. So too, their habitable zone will also rise roughly with the square of temperature. One twice as hot will give about 16 times the light, and that's 4 times the habitable zone. Again, approximately. So why the cutoff at 1300 Kelvin? What makes the L class distinct is its atmospheric chemistry. These worlds are hot enough to vaporize metal oxides such as titanium oxide and vanadium oxide, and to keep iron-bearing silicates aloft as hazy mineral clouds. In cooler red dwarfs, these molecules help define the spectrum, but in L dwarfs they begin breaking apart, raining downward or condensing into exotic layers that resemble a cross between a volcanic plume and a dusty sunset. Early L dwarfs show traces of titanium oxide and vanadium oxide, while mid-range L dwarfs are dominated by thick iron and silicate clouds, and the coolest members of the class begin transitioning toward methane-bearing atmospheres as their visible light fades into the infrared. This is why the L category exists at all, in most temperature regime where atmospheres stop looking like the coolest true stars and start resembling superheated versions of gas giants. Metal oxides vanish, mineral clouds arise and fall, and the chemistry crosses a threshold from stellar to planetary behavior. L dwarfs are the boundary objects, the last red embers before the spectrum drops fully into the infrared, or very nearly so. T-Dwarfs. T-Dwarfs are cooler still, beneath any real claim at being a star, fading into a deep purple-violet dimness as their atmospheres fill with methane. Methane is a voracious absorber of red light, chewing out huge chunks of the spectrum and leaving these objects glowing mainly in the near-infrared. This is why it's such a good or bad greenhouse gas. This is what defines the T-class too, broad methane absorption bands that dominate their spectra, much like those in Jupiter and Saturn but under far higher pressures. The temperature ranges from roughly 700 to 1300 Kelvin, where metals have long since rained out and silicate clouds have sunk beneath the visible layers. What's left is an atmosphere shaped by hydrogen, water vapor, and methane chemistry, essentially a hot Jupiter spectrum running on low power, without the starlight. T-dwarfs to the point where brown dwarfs stop looking like failed stars and start looking like overachieving planets, but with enough mass and pressure to keep their interiors far hotter than the gas giant we know. This is also a temperature range where you can contemplate building actual machinery inside the upper layer of a star, without exotic materials. Akin to the ones for the surface of Venus, they still have to be for very high temperature designs. You also deal with a lot of gravity, 30 to 100 times what we are used to, and any megastructure in there is probably an orbital ring. You could live on an upside-down train, running inside that ring's evacuated superstructure too. Heat is a real issue on superconductors, or any conductor, so you might need a constant energy supply to keep that ring suspended inside that body, but there is a ready power supply at hand. Dim though they are, their surface lighting is 14 to 160 times noontime equatorial lighting on Earth, which runs a lot of solar panels, and there's obviously no night or day here. Y dwarfs. That's less true of Y dwarfs, where temperatures range from about 500 Kelvin down to 250 Kelvin, the latter being more akin to Antarctica than a stellar surface. The brightest Y dwarfs put out only a few times Earth's noontime flux at their photosphere, and even that would look dim to us because almost all of it is infrared. At the cooler end, you're down to the order of 20 watts per square meter, bright for an indoor room, but again almost entirely invisible heat rather than light. Y dwarfs are the coldest and faintest of all, objects barely warmer than a summer day on Earth, glowing so feebly in visible wavelengths that they are effectively black to the naked eye. Their 250 to 500 Kelvin atmospheres enter a regime where water condenses into clouds, ammonia becomes a major absorber, and the overall chemistry starts to resemble the upper layers of Jupiter's atmosphere, just colder, darker, and lonelier. They shine almost entirely in the mid-infrared, radiating only trace amounts of visible light, often no more than the reflected glow of a harvest moon hanging orange and dim in the sky. The faintest Y dwarfs would be nearly impossible to see even from close range. I suspect these would be very popular places to hide, especially the cooler Y dwarfs whose temperatures are not far off from Earth-like conditions, even if their surface gravity remains enormous. Living there probably means being post-biological, operating entirely in orbit, or resorting to tricks like the equatorial train, a ring of habitats and tracks whipping around the dwarf fast enough to give you something closer to comfortable artificial gravity. But they still have more gravity than Jupiter has, which is crushing compared to Earth's. Despite cooling to temperatures rivaling household ovens or Arctic nights, white dwarfs remain the same size as Jupiter. As mentioned earlier, once you reach Jupiter's mass, adding more mass doesn't make you bigger. Degeneracy pressure pushes back, and the object gets denser instead. A white dwarf may weigh 20 times as much as Jupiter, yet be the same diameter. A dark and ultra-compact world, glowing with the last size of its formation heat, and with around 20 times their gravity. Their faintness makes them hard to find, but their sheer numbers make them one of the most common stellar objects in the galaxy, quiet embers drifting through the stars. What they all share, though, is they sit in the uncomfortable middle ground between planets and stars, too massive to be ordinary gas giants, but too small to ever ignite hydrogen fusion. They do get a brief flirtation with stardom. Again, anything above about 13 Jupiter masses can burn deuterium for a few million years. Above 65 Jupiter masses, they can burn lithium too, which is very rare, but neither reaction produces enough energy to lift them into the ranks of real stars. Instead, they glow faintly from gravitational contraction and residual heat, cooling and dimming slowly over the ages. And it is a lot of heat, too. Remember, Earth's core is mostly hot from its own formation, which is trivial compared to the energies released from Jupiter, and yet the Earth's core is hotter than the surface of the Sun. And yes, the decay of things like uranium does help with that temperature too, but those gas giants also have those materials. And these brown dwarfs are not failures so much as a third category, places where nature almost made a star and decided to stop halfway. And as failed stars go, they are surprisingly common. They could outnumber every other star in the Milky Way combined. And despite their faintness, they offer an astonishing range of environments, energy sources, and engineering possibilities, enough that a future civilization might build entire communities around these hidden giants in the deep sky. When we talk about colonizing brown dwarfs, we're exploring places most people barely think of as stars at all, the strange middle ground between planets and suns. A lot of discovery takes place when someone decides to take a closer look at something everyone else has overlooked. One show that approaches that idea from a very different angle is 17 Pages, a documentary about a medical and scientific scam, and the investigation slowly unraveled how it spread and why people believed it. Another series worth checking out is A Bit Obscure, which dives into the creepy and unsettling origins of fairy tales and other stories, exploring the darker folklore and cultural history behind them. And if you enjoy speculative big-picture thinking, my own Nebula exclusive this month is Lazarus Protocols, exploring how civilizations might preserve knowledge, rebuild after extinction-level disasters, or even resurrect lost species, including themselves. You can find all of those on Nebula, the creator-owned stream platform built by the people actually making the content. It's also where every episode of SFIA premieres early and completely ad-free. Use my link or the QR code on the screen to get 50% off an annual plan. Just $30 for the whole year. Habitable Zones. The habitable zone of any star, or substellar object, is the region where liquid water could exist on the surface of an orbiting world. With brown dwarfs, we can call their companions planets or moons interchangeably, the physics is the same. As mentioned earlier, a bright young L0 dwarf has a habitable zone only 1% as far out as our own, about 0.10 AU or 1.5 million kilometers, roughly 930,000 miles. By the time you reach L9, that distance has fallen to 330,000 kilometers or 200,000 miles, closer than our own moon. T-Dwarfs continue this trend, with habitable zones shrinking to the range of 45,000 kilometers or 28,000 miles, not much higher than Earth's geostationary orbit, inside the Roche limit for that object. For the coldest Y9 dwarfs, the Earth flux habitable zone collapses to a mere 15,000 kilometers or 9,000 miles. Long before you get to that point, any world-retaining surface water would be relying heavily on tidal heating, and virtually every habitable zone satellite, except possibly around an L0, would be tidally locked. Probably. L0 dwarfs are a special case. They and the subclasses just on either side of them can actually host an Earth-mass planet or moon with a roughly 24-hour orbital period while still sitting inside their habitable zone. A tidally locked world does not get a 24-hour day from that, of course, unless it's in resonance with some other body or as part of a multi-star system, but you can get some interesting orbital arrangements where the apparent day length remains Earth-like. Below that mass and luminosity, day or year lengths around brown dwarfs compress into hours, not days. Now comes the limiting factor, the Roche limit I mentioned, where a body orbiting too close to a massive primary gets torn apart by tidal forces. Essentially, that object you're orbiting exerts more force on that object orbiting its surface than it itself does. For an Earth density world orbiting a typical brown dwarf, this limit lies around 400,000 to 500,000 kilometers. Early and hotter L-dwarfs can place a planet safely outside that boundary while still keeping in the habitable zone, though tidal effects will be huge. But once you slide down to roughly L6 or L7, the habitable zone has already dipped below the Roche limit. Below about an L7, producing only 10 millionths of the sun's luminosity, the habitable zone collapses inside the region where a rocky planet can survive intact. All that tidal forces also equals tidal heating, so we can fudge that amount a little bit, but only to a point. Anything cooler than that, and habitability no longer means planets basking in the faint glow. It means ward houses, orbital habitats, and megastructures sipping whatever heat the dwarf provides. And you can put a megastructure closer since they're held together by structural strength, not by gravity. This could lead to some amusing evolutionary consequences. If life emerged early, when an L-dwarf was still warm and luminous, a world skirting the Roche limit would experience such strong tidal differences that the gravity on the substellar side would be noticeably lower. Major eruptions or impacts might easily throw dust, spores, or even organic material off the surface and into space, naturally seeding nearby moons, rings, or co-orbiting bodies. One last note on habitability. All these distances are based on bolometric luminosity, which includes the infrared photons that brown dwarfs are best at producing. They do not include tidal heating, which may dominate the energy budget. A sufficiently massive satellite orbiting just outside the Roche limit might maintain liquid water from tides alone, with very little help from the dwarf's radiation. They might also get away with very thick and insulative atmospheres. Visually, such worlds would be dim, perhaps only a tenth or even a hundredth of the Earth's noon illumination, but this is still adequate for photosynthesis, and to human eyes it would look like a permanently overcast day, late afternoon or early twilight, perfectly livable as long as you don't mind the darkness. Megastructures. Habitable planets or atmospheres and possible alien life are all well and good, but ultimately the important part for us is if we can live there and would want to, and here we get to some neat tricks. First, we could easily mine any nearby rings, asteroids, or moons for material to build tons of classic rotating space habitats, and there's an obvious source of fusion fuel nearby, even if the body itself doesn't offer great lighting. As noted, you can ignore the Roche limit for megastructures as they're not a heap of matter sitting together held by its own gravity. There should be no brown dwarf except the dimmest white dwarfs, where a space habitat could not function normally just by using some thin mirrors to concentrate visible light in their habitat regions, while bouncing infrared light off for some other usage like running a heat engine and power plant. Possibly for supplemental lighting. L-dwarfs have a limited lifespan before running low on fuel and turning into T-Dwarfs, but these and L-dwarfs are very long-lived and still have plenty of deuterium floating around if that's what we need for fusion, and the same for helium isotopes. These might all get done up as mini Dyson spheres or swarms too, as all but the dimmest of these bodies gives off a ton of energy at temperatures higher than Earth, allowing its capture and conversion to electricity to run human-comfortable environments. Even a Y6 should be able to run about 10 Earths worth of terrestrial living space. A L0 could support a couple million Earths worth of living space and habitats. Needless to say, post-biologicals can do better as they can operate at lower temperatures. And for clarification on that, you cannot run a heat engine that does not have a higher temperature than the environment that you're trying to run it in. This means brown dwarfs become more than remote ports of call. As we said, they would probably outnumber every other stellar object combined, albeit they'd probably be the galactic equivalent of a one-horse town between cities. But in this case, that one-horse town might support billions to even quadrillions of people, which is a lot more horses. Now we've talked before about using star boosting to enhance the light coming off dimmer stars, and we're going to wrap the episode up by taking this a step further with a pair of new megastructures we'll call the Dawn Belt Array and the Equinox Shell. Here's the basic idea. Star boosting normally takes a dimmer star and places reflective mirrors over its polar regions, bouncing light back down at the star to heat it up. These mirrors are typically statites, ultra-thin reflective sheets that can hover over a point on a star because the radiation pressure pushing outward balances the star's gravity pull inward. And because both gravity and light intensity falls off the inverse square of distance, a statite that floats at one distance can float at any distance, as long as it maintains the right orientation. The difficulty is this trick works best on bright stars, which have high gravity but vastly more radiative power per kilogram. By the time you get down to dim red dwarfs, the situation reverses. Their gravity is still substantial, their light is feeble. A statite around an M9 dwarf has to be incredibly thin, roughly 1,000 times lighter than kitchen aluminum foil, just to hover. And even if you can make a foil thin enough to float and reflect enough to catch the largely infrared output, there's hardly any mass left to host guidance, control, or station-keeping systems. This is where ligites come in, a concept I developed about a decade ago. If a statite is a static satellite, a ligite is a lagging satellite, one that still orbits its primary but does so slower than a purely Keplerian orbit would dictate, because radiation pressure partially counters gravity. Ligites are heavier than statites, but still light enough to be strongly affected by stellar radiation. With modest proportional sail adjustments, they can follow non-Keplerian orbital paths, drifting behind or ahead of where a normal satellite would. Whether you use statites, ligites, or conventional satellites, the trick for a star boosting system is to create mirrors that reflect light when they are over the poles, and not when they pass through the orbital plane of the planets, moons, or habitats. So they flip edge on, letting light pass through whenever they enter that plane, and flip broadside to reflect when they leave it. The result is a full Dyson swarm of mirrors, except one that sends almost all light back onto the star, except where inhabited zones lie. By default the equator, but it doesn't have to be. That concentrated light heats the surface layers of the dwarf, raising its effective temperature and shifting more of its output into visible wavelengths. This does not significantly affect the deep interior of the star. The lower layers are already far hotter than the photosphere, much as Earth's core exceeds the surface temperature of the Sun. You might get a little atmospheric expansion, but nothing dramatic. And this is where we get to the dawn belt array, a mirror swarm that boosts the star's brightness, expands the habitable zone by concentrating its energy into a permanent equatorial band, and provides a bright, warm torus volume around the dwarf for orbital habitats to bask in. And it need not be a complete ring either. You technically only need to flip the mirrors between the light source and any of the bodies you want to get light, and you can alter the ratio to provide noontime summer to redder and dimmer evening lighting. The dawn belt arrays are meant for dimmer red dwarfs and brighter brown dwarfs. Alternatively, the equinox shell is the heavier-handed variation on the same idea. In this version, we wrap orbital rings around the entire brown dwarf, most likely a T-type, though a dim L or bright Y dwarf might work. And people can live inside those upsized train habitats running along the rings that we discussed earlier. More importantly, those rings provide the structural support we need to suspend wide plates of IR-reflective material that completely enclose the dwarf. At that point, you've essentially built a shell world, something we've often discussed doing to Saturn, though the surface gravity on a brown dwarf shell would be absolutely punishing. The main effect of the shell is to warm the dwarf by reflecting its infrared emission back inward, but you can only push that so far before the plating begins to overheat. Tungsten, which reflects IR well and has a high melting point, is a good candidate for the inner surface, though you still want active cooling loops woven through the structure so the shell doesn't start glowing as bright as the dwarf is trying to brighten. Around the equator of the shell, you would embed a thin lens, transparent enough to pass visible light while still reflecting most infrared. It does not have to be perfect. Even a partial transparency gives you substantial power generation and a steady trickle of life-appropriate daylight emerging from a star that would otherwise be nearly invisible. And if you're willing to push the engineering even harder, you could attempt something more ambitious. Increase the internal pressure of the brown dwarf itself. By heating and compressing the outer layers, or by using the enormous magnetic fields already present for starlifting, you might nudge the core back into deuterium fusion, or in the extreme, even towards sustained hydrogen fusion. As the surface heats, the dwarf produces a stronger solar wind, which you can then harvest by standard starlifting methods. All those powerful superconducting magnets doing the lifting might also serve as tools that squeeze a failed star a little closer to becoming a real one. It should be possible to vary your shell diameter too, as your light changes, or even to pump parts of it in and out like a big heart, which is appropriate as it would be the heart of that civilization. Definitely more effort intensive as methods go, but it might be a good approach. As we like to say here, if brute force isn't working, you're not using enough of it. Even the dimmest corners of the galaxy, life and civilization has room to grow. Brown dwarfs may never blaze like a real star, when their quiet glow lies in invitation, energy that lasts for trillions of years, stable gravitational wells for habitats and industry, and a canvas wide open for engineering as modest as a waypoint station or as bold as a dawn belt array or the equinox shell. They are the hearths of the future, the flickering embers that might outlast every ordinary star. And there's one thing our species has always been good at, is turning embers into bonfires. So whether we settle them for refuge, for exploration, or simply for the joy of making something where nature left nothing, these failed stars may yet become some of humanity's greatest successes. After all, the universe is vast, the night is long, and we've never been shy about bringing our own light.